let's wrap up this problem that we started on. Remember, we're doing a two-body 2D problem, and you'll have one of these on the next test with two bodies, two dimensions. Really, it's very similar to what we did before on the last exam, where we had the two bodies in one dimension. Really, the only difference is, well, there are a couple differences. One is that you have to resolve the forces, and then because you're resolving the forces into the x and y components, you have forces in the x direction and in the y direction. Instead of two equations, now you're going to get four equations because you'll get the sum of the forces in the x and the sum of the forces in the y for one body and then also for a second body. So the process is still the same. That is that you label all your forces in the x and y directions, then you resolve your forces on your free body diagram, and then you apply Newton's second law. Those steps still remain the same, with the one added thing is that we're resolving the forces into their x and y components. However, I mean, that said, they're largely the same. They're also a little more complicated, just because you have more equations to solve. Okay. We wrapped up here last time. We wrote the sum of the forces in the x and the y for both bodies A and B. And then I also added these other two equations. Now let's go through and figure out, well, what are some of the things that I can begin to fill in here? Um, I can figure out what the normal force is right here, because I know that the weight of the normal force, or the weight of that object B, is 20 newtons. So Fn is equal to Fwb, and that's equal to 20 newtons. That comes only from the sum of the forces in the y direction. And then that's going to be sort of the end of what we use that equation for, that the normal force is equal to 20 newtons. However, then I can use that and determine what is the static frictional force. So Fs, that is acting on that block, is equal to mu s times the normal force. Mu s was equal to 0.2 times the normal force, which is 20 newtons. And so that's equal to 4 newtons. So just to return to what we were thinking, what we're trying to figure out here, there is some maximum weight that you can apply here that will keep this stationary. And the maximum weight will occur when the static friction is at its maximum value. So this 4 newtons that we found down here, that is the maximum value for the static friction. Once you exceed that, it's going to set this block into motion. And so we want to figure out what is this weight that will, the maximum weight here, that will still keep this block stationary. And so we need to know what is that maximum static frictional force. All right, so now we know the static frictional force. Now we can begin to identify some of the things that are unknown. In this equation, all that we don't know is Ft1. So in fact, now we can identify what Ft1 is, because look at this equation. I just have Ft1 is equal to Fs. And so that's equal to 4 newtons. So I've done all that I can with these equations on the left. Now let's look at the equations on the right. What are our unknowns here? In both of these cases, these are equal to 0. My unknowns are Ft2, Ft2, and Fwa. I know what Ft1 is, so I can figure out what Ft2 is. And then once I find out Ft2, I can solve for Fwa. So this is fairly simple substitution. You could have a more complicated substitution though, and we'll see some, where I have two unknowns in this equation and two unknowns in this equation. But in this case, I only have one unknown. So I can solve this for that one unknown and then plug it in here in order to find what is my my FWA, which is what I want to know. Kind of my notes here. All right, so to solve this for FT2, FT2 equals Ft1, this is equal to 0, divided by cosine of 30. That is 4 newtons over cosine 30. And then that's equal to 4.6 newtons. So that is the tension in this rope that was at an angle. FT2 is that tension. Now I can take this and I can plug it in here and I can find FWA. FWA is equal to FT2 sine 30. And that's equal to 2.3 newtons. Yeah, half of 4.6 or 2.3 newtons. So that is the value that I'm looking for. That is the weight of block A that will keep it stationary. Now, usually on these problems, and I'll do this for you too, and I did that here, I said 3 points, but I'll give you 5 points extra credit. If you can solve this system of equations with Gaussian elimination, um, let me show you how that works. This one is actually not that hard because the matrix that you set up is not terribly difficult to solve. But this is useful when you have a system of equations to solve it in this way that I'll show you. When I show you, you're probably going to say, yeah, that was a lot harder than solving it by substitution. It required a lot more steps. But it's useful because it's a method that's easily automated, that you have algorithms that allow you to solve a system of equations to automate it. And then it's also easily scalable. So here we're only solving for a couple of unknowns, FT2 and FWA. Those are the only unknowns that we're solving for. But by this method, you can solve for hundreds or thousands or even millions of unknowns with a computer. And so that makes it a lot easier. You'll learn how to do this if you take numerical analysis, if you go on and get, a math minor as you chem majors. Engineering majors, depending, if you go on to graduate school, you'll probably see this in solving various systems. So when you solve a system of equations by Gaussian elimination, you first want to set up your equations in a matrix form. I'm going to write these two equations right here in a particular way. I'm just going to rewrite them down here. I'll say the sine of 30 times FT2 minus FWA equals 0. And then I'm also going to say the cosine of 30 FT2 plus 0 FWA equals 0. I just set them up so that I have like variables in the same position. And then I'm going to write the coefficients of these variables as a matrix with this as an augment to the matrix. So all I'm doing is I will say the sine of 30 is 0.5. The cosine of 30 is 0.87. The coefficient for this minus FWA is -1. And the coefficient for the 0 FWA is 0. This is a matrix, but now I'm also going to augment the matrix, which means I add another column, and the augment to this matrix is a 0, 0. All I've done here, if you've seen matrices, this is probably familiar to you if you take linear algebra or numerical analysis. If not, that's okay. All I've done is I've just taken the coefficients of the variables, including the negative signs when it's relevant, like with this -1, and I put them in this grid-like fashion. This is equation 1, this is equation 2. And it allows us to work with those equations in a different way. Now, what I want to do is to produce what we call an identity matrix. An identity matrix looks like this. It has a 1 and a 0 and a 0 and a 1. And then you have your augment over here. And the identity matrix will tell us what each of these variables are. So this row will tell you what the first variable is. It would be like 1 FT2 plus 0 FWA equals whatever the value is. Right, so that tells you what FT2 is. And then this one will tell you what FWA is. Right, 0 FT2 plus 1 FWA equals whatever value. So we're going to take this matrix and put it in this form, and whatever the values are here will be the answers for FT2 and FWA. Okay? Now there are some rules how I can take that first matrix and change the values. Let's see, the rules are I can switch rows, or I can multiply a row by a scalar, by a number, or a scalar, just a scalar quantity, I can multiply a row by a number, or I can divide a row. I can add two rows and replace it. So I can say, replace this row with the sum of this row plus this row. Or I can add two rows and replace a row. And that's really it. Those are really the only things that we'll do, is that I'll multiply two rows, multiply or divide a row by a value, and then I can add two rows and replace it with another row. So let me show you how that works out here. Let's say first I want to look at, say, this row, and I want to make it more in the form of the identity matrix. I'm going to do a couple things. First, I'm going to take this row, I'm going to move it up here, and then I'm going to do what to this row in order to put it in the form of my identity matrix. What will I do to it? Remember, I can multiply or divide rows by a number. So what would I do to this row in order to make it more in the form of an identity? Right, I can divide this row by 0.87, and then I'll move it up here. So let's see, looks like I had a mistake up here, that this is not equal to 0, but it's equal to 4. Sorry about that. Let me fix this. So right here, this is equal to 4. Because that comes back from our equation, where was it? The ft2 cosine 30, right here. Because I know that ft1 is equal to 4. Is that right? Yeah, ft1 I found was equal to 4. So I'm just going to put a 4 there. That means that down here, I get 4 instead of 0. All right, so I'm going to divide that second row, row 2, by 0.87, and move it to the first row, to row 1. And so it's going to be 0.87 divided by 4, 0, 1, and then I'll still have 0.5, negative 1, and 0. Should be 0.87. And so that gives me 0.87 divided by 4 is, what is it? No, I'm sorry, y'all. Not 0.87 divided by 4. 0.87 divided by 0.87. So I'm going to have 0.87 divided by 0.87 will be 1. And then over here I'll have 4 divided by 0.87. So I'm going to have 1, 0. 4 divided by 0.87 is 4.6. And then down here I'll have 0.5, negative 1, and 0. Okay, now I want to get this row into more the form of this 0, 1. And so what I'm going to do is I'll multiply this row by negative 0.5 and then add it to this row. So I get negative 0.5 times 1 added to 0.5 will be 0. So I'm going to take row 2 and add it to negative 1/2 times row 1. And then I'm going to replace that with row 2. So I'll still get 1, 0, 4.6 here. And then I'm going to add 0.5 plus negative 1/2 times 1, right, which will become 0. Here, this just still is negative 1 because I'm adding 0 to it. And over here, I get 0 plus negative 1/2 of 4.6. So that is, I now get 1, 0, 4.6. I get 0, negative 1, negative 2.3. And I'm almost into the identity matrix. Remember, my identity matrix is going to be 1, 0, 0, 1, and then the augment here will be the answers. What's the final step here in making this into an identity matrix? What do I have to do in order to form this into that 1001 format? Divide by -1 or multiply by -1. Either would be correct. So if I multiply this row by -1 and replace it with the value of that, so I'm going to take row 2, multiply it times -1, and replace row 2 with that value, and I get 104.6, 2.3. These then are the answers for FT1, or was it FT2 and FW. Okay? So, on the exam, you'll have extra credit that you can do this. If you look back on some of the old exams, I'll work through other examples. But I'll try to make the values work out easily for you. I just want to see that you can do this in this way. It's not terribly important for this course, but it is an important thing if you go on into graduate school that you know how to solve large systems of equations, depending on what you're going to, especially your engineering majors, even your chemistry majors. Uh, it's not uncommon to take millions of equations and want to solve those equations for millions of unknowns. Like if you're looking at, say, the movement of particles, or if you're looking at you're building structures that have lots of different variables associated with them, it is important to be able to solve systems of equations in this way. And when you can do it this way, this is easily programmable and able to solve even larger systems. Okay? Extra credit, not required for you to do, but it is useful. I'll give you 5 points. I found that in the past that many students don't do it. I don't know. They just get sort of bogged down in other stuff. But if you're willing to spend a half hour on it and master it, it'll be something similar to this difficulty. It'll be worth 5 points on the exam. Okay, let's do some more 2D problems. Let's do an inclined plane. Here, first, let's look at adding a frictional force. I don't think that we've had friction on an inclined plane yet. I don't think we have. Let's go back and see. We did that problem. No, it doesn't look like we've had friction on an inclined plane. We've done friction, but not friction on an inclined plane. So let's think about this first, just sort of conceptually. If I have an inclined plane, and I have it at an angle theta, we'll say theta is, say, 30 degrees. I want to know, how does the friction depend upon the other forces? So how is the frictional force affected if the angle theta is increased? Let's say that this angle theta is 30 degrees. That means that this angle is 60 degrees. And if I draw my coordinate system over here, I can redraw my forces. I have Fn, Fs, I have Fw cosine 30, excuse me, Fw sine of 60, which is the same, by the way, as Fw cosine 30 as we talked about last time. And then here I would have Fw cosine of 60. So what I've done there, this is stuff we've seen, but I've resolved my force weight into its x and y components, remembering that my angle here is 60 degrees, not 30 degrees, because I take the angle from the x-axis. This is my coordinate system. There's my y. There's my x. Notice that I have a triangle here. So if this angle is 30, this angle is 90 minus 30, or 60. So how is the frictional force affected? There are a couple things that happen that cause the frictional force to change. As I move this inclined plane up, as I increase the angle, two things happen. Two values will either increase or decrease. First of all, the x component of the force, Fwx. As theta increases, what happens to Fwx? Does it A, go up, or B, go down? Fwx. As theta increases, as I move the inclined plane up, what happens to the x component of the force? Does the x component of the force weight go up or does it go down? Let's do a little bit longer. So click in what you think, A or B. All right. I'm going to stop at 45. Okay, so we're sort of split as to what happens. We'll come back to that, but also let's think about what happens to the normal force. This is a little more intuitive, I think. Does the normal force, as theta increases, does it go up or does it go down? What happens to the normal force? Remember, the normal force is the force that pushes on the block from the surface. Does the normal force go up or does it go down? And when we're talking about theta increasing, I'm talking about this angle. So as this thing comes up, what happens to the normal force? Does the normal force increase or the normal force decrease? I'm going to stop at 32. Okay, let's see. Normal force will actually decrease. So B is right there. And the weight, the x component of the weight, that is the component of the force weight that is in the x direction, will increase. So A is the right answer. It's a little tricky on this first one because there are a couple things going on. This angle is increasing, and that causes this angle to what? Increase or decrease? Decrease. Now think about as your angle goes from 0 to 90, which is what we're doing, what happens to the cosine of the angle theta? Or let's say it goes from 90 to 0. What happens to theta, cosine of theta, as we go from 90 to 0? It gets bigger, right? It goes from 0 to 1, the cosine of the angle. And so as this angle gets smaller, it's getting closer and closer to cosine of 0. And the cosine of 0 is equal to 1. When it goes all the way up, then FWX is going to equal to FW. But you might be a little misled too because, well, that seems like the weight would all be in the vertical direction. But remember that we've chosen our x component of our force to be, or our x coordinate, our x direction to be along the plane of the incline. And so as that plane of the incline goes up, then FWX will increase and our normal force will decrease. The normal force, I think, is a little more intuitive because if I have an object, that's on a vertical plane, there is no normal force here because the weight's not acting into this plane at all. And so as my inclined plane goes up and up and up, then it causes the normal force to decrease. All right, so how does this affect the static frictional force? Well, in this case, the static frictional force will be caused to go up or down. Now look at our free body diagram here. Notice how these things are situated with one another, how our static frictional force is related to the weight. Is it going to cause, when FWX goes up, what is that going to cause the static frictional force to do? Increase or decrease? Or what, Brennan? Increase is right, that the static frictional force will increase. Because look, FW cosine 60, that is FWX, minus FS equals 0. These two are equal in magnitude, opposite in direction. So as this increases, this also increases. So this will cause it to increase. However, the normal force, as it goes down, how does that affect static friction? It's going to cause it to decrease, because remember, static friction is dependent upon the normal force in this way. So this will cause our static friction to decrease. All right, so a couple things. As our object is on our inclined plane, at first it is there so that the static friction holds it onto the inclined plane. And then as you increase it more and more, it needs a greater static frictional force to hold it on the plane. But as the normal force is decreasing, that maximum static frictional force is also decreasing. And then eventually you just get it to a point where it slides off. All right? Likely you will have an inclined plane with static friction on it. You're going to have at least one two-body 2D problem, and it will likely be a inclined plane. It could be like one that we did before with the two blocks. That would also be a two-body 2D problem, but you could also have an inclined plane with friction on it. Let's work a problem like that. Your problem will not be quite like this. Yours will have other bodies associated with it, but it's important that you master this problem in order to be able to work those problems. So let's consider here I have an inclined plane. We'll say that it's a 30-degree plane, and I just want to know what is the minimum coefficient of static friction so that this thing will stay on the inclined plane without sliding off. The mass of this block, it says, is 10 kilograms. So I can say that the weight is 100 newtons. If this angle is 30, this angle is 60 degrees. Notice here's my x. This is the positive x. This is the negative x. I think I mentioned this last time. I'm pretty sure I did. Be careful that the positive x, in this case, is down the inclined plane. The negative x is up the inclined plane. That's important if you have an accelerating system, because you need to know whether it's in the positive direction, your acceleration, or in the negative direction. But also be aware that if I flip the inclined plane in the other direction, then the signs for this also flips. Did I go over that last time with y'all? I think I did. Let me just sort of recap it right quick. So if I flip this inclined plane, notice now my x direction, this is plus x and this is minus x. The y is always going to be the same, but the x can change depending on the orientation of your inclined plane. Okay, draw your free body diagram, resolve your forces, and write Newton's second law. So I'll give you a second to catch up and to draw your free body diagram. Draw all the forces that are acting upon it, and then resolve those forces that are not on axis. In this case, it's just the weight onto its x and y components. Alrighty, let's see, we have our normal force, which is up. We have Fs, which is in the negative x direction. We have our x and y components of Fw. What's this? Cosine of 60. Fw sine of 60. Now write your Newton's laws. Sum of the forces in the x equals max. Sum of the forces in the y equals may. I'm going to keep those accelerations for now, because if it's static or dynamic, it's going to be all the same up to this point when we would actually write our accelerations as 0 or non-zero. Sum of the forces in the x is Fw cosine 60 minus Fs equals, and I'll write 0 here because our acceleration is 0. And then sum of the forces in the y is Fn minus Fw sine 60. And that's also equal to 0. It'll always be 0 for our inclined plane. The y motion will always be 0 acceleration. That's the That's the beauty of drawing our coordinate system in the way that we have, that the acceleration in the y direction is always 0, because we take that y direction to be perpendicular to the surface. Okay, so we can make short shrift of this. Our static friction is Fw cosine 60. That's 100 cosine of 60. Is that a half? That's a half, right? Is that 50? Am I right about that? Or 86? It's 50. Okay. And then here we can also find our Fn, which is Fw sine of 60. That's going to be 100 times sine of 60, which is 87 newtons. And then how do we find our coefficient in this case? Find the coefficient. We know that our static frictional force, our maximum static frictional force, is equal to mu s times the normal force. I wrote it as an equality because we're looking for the maximum static frictional force, which would tell us what our mu is. And so mu is 50 over 87, which is approximately 0.6, I think. Is that right? Somebody tell me? Okay, we'll call it 0.6. Emma? Now, I put this Fs is equal to 100 cosine 60. This came about from my three-body diagram, that these two forces, because the acceleration is 0, are equal and opposite. This minus this equals 0. And so Fs is equal to the x component of the weight, which is 50 newtons. The normal force is the y component of the weight, which is 87 newtons. I did that right? Did I do that right? Yeah. Is that clear, Emma? Yeah. And then I find mu s. So you need to know this backwards and forwards, because you'll have an inclined plane, but it'll have other things going on in it. But this will be going on as well. And so you need to know this, pretty well, how the static friction and the weight are related to one another, and how the normal force and the weight are related to one another. You don't have to memorize it, but know this procedure. I draw my forces, I resolve them into their x and y components, and then I apply Newton's second law. In this case, I get a fairly straightforward system of equations to solve. Straightforward in that there's only one unknown in each equation. Okay? All right, yeah, Nicole. No, good question. So she said, will the forces in the x direction always be the same? And that goes back to right here. This is sort of where we diverge from a dynamic problem, because in this case, only because the acceleration is 0 are the forces in the x direction the same. This is a static problem. You could have either a static or a dynamic problem. A dynamic problem, which will work, is one where it's accelerating, and we'll see one where it is accelerating, where this is not true, where it's equal to some value right here. Now, in the y direction, this will always be true for an inclined plane. It's never going to accelerate in the y direction, because it would fly off the inclined plane. Okay, good question. We'll see an example like that, and you could see either one, or both. Let's see. There's some more space. Let's try this. I want y'all to try this. What is the normal force acting on this block? 10-kilogram block. If you finish this one, go on to the next one, which is, I think, yeah, what is the coefficient required? Was this exactly the same as what we did? Oh, I'm sorry. I meant to change up the numbers on that. But I'm going to skip this problem. So it's exactly the same. But I'll leave you. You can work it on your own just for extra practice if you want. But it's exactly the same as what we did. Let's do this one. This is a two-body problem. Notice that it's accelerating. Be careful as to which direction it's accelerating. If you draw your x plane along this direction, is it positive or negative? And we're going to follow the same procedure. I have a tension. I have a tension in this rope. The tension that's felt here, by the way, is the same as the tension that's felt here. And I want to know what is the normal force acting on this block, what is the frictional force acting on this block, and then also what is the acceleration of this block. So I want to know what is the acceleration. I give you the two masses, I give you the coefficient, and I give you the angle. So now I want to know what is the acceleration of this system. All right, I'm going to let you get ahead just a little bit, but I want you to first label all the forces on M1 and M2. Remembering, like on the last exam, this tension is the same for M2 in magnitude as it is here. Now notice the signs of the tension are going to be different because you'll have different coordinate systems, but the value will be the same. Just going to start drawing in a few things, but you continue on doing your work. Think about the direction of your friction. I haven't drawn it here, so think about the direction of your friction. So these are all forces that we've seen already. I'm substituting here Ft, which is the force pulling it up. What is the direction of our kinetic friction? All right, what force am I missing on the right-hand free body diagram or the right-hand force diagram? What what force am I missing? The frictional force. Is it up or down the inclined plane? It's down. Because it's moving up the inclined plane, our frictional force will always oppose the direction of motion. So it's going to look like this, Fk. All right, remember that I know some of these things, like Fw1 is 21 newtons, Fw2 is 5 newtons. I know that because the masses are given up here. I just multiply them times 10. I also know mu k is equal to zero point 0.4, or zero point 0.4. Okay, now we take it step by step, and I lay it out here so that it sort of helps you in the process. But now that I'm going to resolve my vectors, I have Fn, I have Ft, Fk, and we need to resolve our our weight vectors. So this will be Fw2 sine of 60 and Fw2 cosine 60. All right, now I'm going to write my equations. Now, and I'm not going to redraw this one, but this is our second free body diagram. Now I can write some equations. I'm going to take this first one first, and I'll say Ft minus Fw1 equals M1A. And here I need to be very careful that I keep the proper subscripts, that I keep an M1 here and an FW1, because I'm talking about block M1, not M2. So I need to be careful with that. And then look at the sum of the forces over here. I'll get Ft or rather Fk plus Fw2 cosine 60 minus Ft equals to M2 times the acceleration. Then I also have, in the y direction, Fn minus Fw2 sine 60 equals M2A, but this is in the y direction, so this is equal to 0. So I just get rid of that and say that it's 0. It'll always be 0 in the y direction. Okay, the first two questions you can probably answer fairly straightforwardly. Right, how do I find the normal force? Can I find the normal force from the first, second, or third equation? First, second, or third? I can find it from the third, because I know Fw, that's going to be Fw2, and I know the angle. So for the first part, I just say that Fn is equal to Fw2 times sine 60. Fw2 is 5 newtons times 0.86, so that's 4.3 newtons. So that's the answer to part A. And then if I want to know the kinetic frictional force, how can I find the kinetic frictional force? Well, I know the normal force. What else do I need to find the kinetic frictional force? Not the tension. Now you're thinking in a good way, I like that, but I can find it in a different way, that if I know my normal force, what else do I need to find the kinetic frictional force? I need to know mu k. And then that'll tell me the actual value for the kinetic frictional force. And I like what you were thinking, that you need to know the tension, but you're thinking in the sense of static frictional force, that the static frictional force will change in order to counterbalance whatever force it's acting against, but the kinetic frictional force doesn't do that. It is what it is. It's in motion, it's accelerating at some speed, it's always going to be constant. So the kinetic frictional force is equal to mu k times the normal force. I think mu k was 0.4 times 4.3 newtons. I don't have that value written down. Somebody can tell me. 1.7 newtons. Okay? And now the hard part of this problem is finding the acceleration of block number 2. Well, let's look at our equations. These are all of our equations. Actually, right now, we fully exhausted this third equation, so I'm just going to take it out. You can leave it because we needed it to find the normal force, and we needed it, well, we just needed to find the normal force. But now if I look at these, and I want to know the acceleration, notice both of them have the accelerations here. What's another unknown in this system of equations that I need to solve for? And I don't know. What's another unknown here? Ft. I don't know Ft, but those are the only unknowns that I have. I don't know A, and I don't know Ft. Ft, and I don't know A. And so I want to solve these for A. You can do this in a variety of ways, but first I'm going to rewrite them and just put in the values that I know. I have Ft minus Fw1, which was 21 newtons, equals 2.1A. And then I have Fk, which is 1.7, plus Fw2 cosine 60. That's going to be 2.5 plus 1.7 minus Ft equals to, is into 0.5, yeah, 0.5a. Okay, this is a system of equations just like we had before. You could solve it by that Gaussian elimination, um, where you would write it as, I'm not going to do it here, but you could write it as ft minus 2.1a equals 21. And that would be the first line of your matrix, 1, negative 2.1, 21. And then this would be ft plus 0.5a equals to 1.7 plus 2.5. What's that? 4.2. So you would begin here. If you want to do that Gaussian elimination, you'd create a matrix with 1, negative 2, 21, 1.5, 4.2, and then go through the steps of solving that. Here we'll do it by substitution. I think we have time. I'll let you start this, but what you want to do is set one of these equations equal to ft, and then substitute it into the other. There's really no better way to do this for either one. It's going to be about the same difficulty. But we want to know a, so let's say we solve this one for ft. We'd have ft equals 21 plus 2.1a, and then substitute it in here for ft, and then we can solve that system for a, which is the value we want to know. So go ahead and start that, and I'll jump in just a moment. Solve your first equation for a, or excuse me, for ft, because you want to solve for a, and substitute it into the second equation. All right, I'm going to solve this one for a, excuse me, for ft, and then I'm going to take this and plug it in here. And then I can solve that for a. Um, 6 point something, I think. What is it? 6.5. And it comes out negative, correct? Negative 6.5, which jives well with what we know. What'd you get? That's wrong, yes. Okay. That is right. 6.5 meters per second squared. It's negative, which as we should expect it to be negative, if we look back at our diagram, because we know that this thing, or we suspect that this thing, because this is such a more massive block, it's 21 newtons, whereas this is only 5 newtons. We suspect that it's going to be traveling downward like this. And so we find the acceleration to be downward here. We find it to be negative here as well. Alrighty? Let's do a few clicker questions while we're wrapping up. Again, you can find more practice problems on the old exams. Two-body, 2D problem. You'll have it on the exam in a couple of weeks. Let's do a few of the clicker problems. We're only going to look at the 2D problems. There are fewer of those. I understand that we skip some of these. I make up for it when I calculate your class participation score. I just sort of make everything count more. But let's try some of these. Below you see two cases, pulling or pushing a sled with a force F. In which case is the normal force greater? In case 1, case 2, or is the normal force the same for both, or does it depend on other factors? So in one case, case 1, I'm pushing down like this. In another case, I'm pulling up like this. I want to know when is the normal force force greater. All right, just a few more seconds. I'll stop at 1 minute. Okay, good. In case number 1, it is greater. It's because the force that you're pushing down on, it has a component in the y direction, Fy, and that contributes to the normal force. And then you also have Fwy. So you have two forces that are pushing down, the weight and you pushing down. All right, in this case, in which of these cases you have two blocks, one on a horizontal surface, one on an inclined plane. In which case is the normal force greater? A, B, or is it the same? Is the normal force both the same, equal to the weight, somewhere less than the weight, or are they both equal to 0? Which case is the normal force greater? All right, I'll stop at 40. Okay, good. A is right. On a horizontal surface, the normal force is equal to the weight. On an inclined plane, it's equal to the sum component of the weight, the sine of the angle theta. Let's skip these. We're going to get to this later. I think that might be it, actually. Yeah, that's all. All right. So as you're looking at those concept tests, just focus on the 2D problems. There aren't that many. I have your exam if you didn't get it last time, okay? But otherwise, y'all have a great day. I'll see you on Wednesday.